Hello everyone, and thank you for attending today's webinar on Overcurrent for feeder protection. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner of the slide area box. If you have any questions during the webcast, just click that Q&A widget at the bottom of your screen. We'll answer as many questions as possible after the presentation. For the best viewing experience, we recommend using a wired internet connection and closing any programs or browser sessions running in the background that could cause issues. Webinars are bandwidth intensive, so closing any unnecessary browser tabs will help conserve your bandwidth. For the best audio quality, please make sure your computer speakers or your headset are turned on and the volume is up. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are running behind at any time, pushing F5 or refresh on your keyboard will refresh the page. You can find additional answers to some common technical issues located in the Help widget at the bottom of your screen. I'd now like to turn the presentation over to Terrence Smith, Commercial Application Director for Grid Automation. Terry, the floor is yours.
Thank you, Colleen, and to all the attendees out there, thank you for attending. Today's session is the first of a series of sessions that we intend to do on some basics of protection. So we're calling these and branding these Tech Talks. And so again, thank you for attending. We're targeting this at about an hour. Before we get started, let me introduce myself. So I lead the team of commercial application engineers for GE's Protection and Control Suite for North America. And I've been with GE for about 10 years. Prior to joining GE, I worked for the Tennessee Valley Authority, and prior to that, I worked for Mesa Associates. I herald from the volunteer state, and I went to the University of Tennessee at Chattanooga, graduating in 1993. So today, what we're really going to talk about and spend most of our time on is some of the very basics of overcurrent protection. So what I intend to talk about are some of the types of overcurrent protection, how we coordinate protection so that we don't overtrip or undertrip, and also some of the GE overcurrent protection solutions and some of the products that we have that will provide this type of protection. And then we'll close with conclusions, and then we'll have some time for Q&A at the end. Before we jump into that, though, when we typically have a distribution system, we have a protection problem. And if we look at this distribution system here, you can sort of see the protection problem that we have. We have multiple devices that would see the fault that I show on this tap off of this feeder on the third circuit breaker, 52.3. So if we look at that, the protective relay that is on 52.3 would actually, which we want to trip, it's going to see the fault, but also the protective relay up at the main circuit breaker, 52M, just below the transformer, it's also going to see the fault. And then if we look through the transformer, there is also a 52U that will see the fault. So all of these relays will see the fault. And we only want to trip as small a section as possible. And in reality, there's actually a fuse below 52.3. So really, we would rather have that fuse below than to trip 52M, for example. So imagine if we trip 52M. If we trip 52M, what we're going to do is we're going to lose the loads that are on 52.1 and 52.2. And so that is called overtripping. We tripped more than we needed to. So really our problem is to only trip the affected section, or to only remove the affected section that has a fault on it. But then that problem is compounded because all of these devices are going to see the fault. We know that they're all going to see the fault because of Thevenin's node rule, right? So the current's flowing through all of these devices to get down to the fault. So we have to in some way coordinate these devices to only trip the affected section. So the way that we typically do that, and the way that we've done that for 100 years, is with time overcurrent protection. And that's what we'll talk about for most of this presentation, is how we time coordinate these protective elements so that we don't overtrip and we clear the fault. Now this does create an additional problem for us, is because we're going to have to slow down the protection on some of these upstream feeders. So for example, the relay that's on 52M, its time overcurrent elements will have to be slower than the time overcurrent elements that are at 52.3. Likewise, the time overcurrent elements at 52U are going to have to be slower than the time overcurrent elements at 52M. So as we stack up these time overcurrent elements, we create more of a time delay, which is not necessarily good. That creates arc flash incident energy issues that we may have to deal with. It also means that the fault is going to be there longer than we might want it to. But nonetheless, that's what we're going to do with time overcurrent protection. So let's talk about some of the types of overcurrent protection. The simplest form of overcurrent protection is just an instantaneous overcurrent protection. And if we look at the evolution of overcurrent and even the evolution of protective relaying itself, this was probably the first type of overcurrent device or overcurrent relay that appeared on the scene. And this, in an electromechanical world, back 100 years ago or so, looked basically like a plunger relay. So it was a coil with a plunger in it. And basically the way this thing operates, and even operates today, even if it's inside of a microprocessor-based relay, is that once the current that is measured by the relay gets above a pickup setting, once it gets above that pickup setting, the element operates with no intentional time delay. So as we look at this graph, time is along the y-axis and currents along the x-axis, and the operate region is any fault current that is beyond the pickup setting that we show with the black line there. And it's even marked as the operate region. Now, on all of these types of protection that I mentioned, that I'm about to mention, all of these types of protection, I'm talking about the intentional time delay. There's also a time delay to clear the fault for the actual operation of the breaker. So the breaker is probably sitting there with a 3-cycle breaker, so there's that time to actually clear the fault as well. Also, even with an instantaneous overcurrent, we have no intentional time delay, but there is some time for that element to operate. So typically, we're doing something like doing a Fourier transform of the sampled values and turning that into a magnitude that we can run through a comparator. So that magnitude calculation also takes some time. That's about a cycle or so. But with instantaneous, there's no intentional time delay. The other type of protection that we will employ is time overcurrent protection. So in time overcurrent protection, what we will do is we will pick a curve, like the curve that we see here, and then that curve setting will be a protective setting inside of the relay, and there will be a pickup setting. There will also be a time dial setting. And so what this does is it allows us to coordinate with some other curves downstream or upstream. So again, this is time along the y-axis, and pick up along, time along the y-axis and pick up along the x-axis. So another key concept that we should keep in mind is also the type of protection. Now, there are multiple types of protective elements that we can use with overcurrent. But what I've talked about so far is just the overcurrent elements themselves, but the overcurrent elements can be things like phase overcurrent. They can also be things like ground or neutral overcurrent. So phase overcurrent is fairly simple. What phase overcurrent is phase overcurrent is an overcurrent element that is operating from the phase CTs. So this is A, B, and C phase. Now, what neutral overcurrent is neutral for GE relays. Neutral overcurrent elements are the calculated 3I0. So it's the calculated vector sum of the phase currents. That's for GE relays. And there are typically neutral overcurrent elements there inside of the relay. Now, in addition to neutral overcurrent, we can also have ground overcurrents. And these can be ground instantaneous overcurrents or ground time overcurrents, the same with neutral. But there are, for GE relays, a ground overcurrent is an input into the relay. And I show a couple of ways that we can wire this input into the relay. The way on the left side of the screen is a residual connection. And so what we're going to do here is we're going to wire all of the phase CTs into and out of the relay, and then we're going to sum the residual of those CTs and take that summation into the ground input on the relay. Now this is fundamentally no different than the calculation of neutral current. So we're actually sort of measuring neutral there, because instead of having the relay calculate the vector sum, we're going to calculate that vector sum with the summation of our CTs. The other way that we can do this is with the zero sequence CT connection that I show on the right. Now the zero sequence CT is different because what it's going to do is it's going to be a large CT, and that CT will encompass all three of the phases. So the magnetic flux that is going to be driven into the core of that CT is the vector sum of the three phases. So this is a very accurate way to measure ground fault current. Now, the key difference between these two, which one of these methods we use, will depend heavily on the type of grounding we have. So imagine if you have these CTs on the left on the phase are 3005 CTs. And those are 3005 CTs, and we have engineered the ground fault current at this facility with a grounding resistor or a grounding transformer, some mechanism like that, to a few hundred amps. Well, we know that the C37 guides that describe how we build and model CTs say that when we're in the linear portion of that CT, in the linear portion of its excitation curve, we could have as much as 10% error. Well, 10% of 3,000 amps is 300 amps. So we could have error on the CTs that was greater than our actual available ground fault current. So for that sort of system, we wouldn't want to use this residual ground connection. However, if this is a solidly grounded system and our ground fault current is 10,000 or 20,000 amps, then there's no problem in using that type of connection. Likewise, if we have the zero sequence CT connection, if we have an engineered ground fault of a few hundred amps, we can easily see that with the small ratios that will typically be available in the zero sequence CTs. Typically, those zero sequence CTs are some ratio like 50 to 100 to 5. So even if it's 100 to 5, though, if we have 10,000 amps of available fault current, that CT would saturate and wouldn't be a good solution for that solidly grounded system. So we want to really choose our CT methods and our ground fault methods based on the available ground fault current and how we are actually grounded. Another type of overcurrent protection that we might employ is a definite time overcurrent. So a definite time overcurrent is simply the instantaneous time overcurrent that has had an intentional time delay added. So this is one of the mechanisms that we can use to start to time coordinate the overcurrent protection. So if we look at this system below in the bottom of the slide, and you see breaker A and breaker B, one of the concepts of protective relaying that is very important is the reach of the relay. Now, normally when we talk about reach, we're talking about distance elements and things like that, but all relays have a reach. And so when I say reach, that is how far into the power system the relay can see a fault. So if we look at these two relays, the relay at A sees all the way past the fault location and overreaches the relay at B. So since it overreaches the relay at breaker B, we need to coordinate these two curves. So we can do that with a definite time delay, and we'll make the curve at the blue curve a longer time delay than the red curve. And so that's what you see here in the time current curve just above the power system. But typically what we do is instead of having a definite time overcurrent, we'll have time overcurrents. And so time overcurrents will take the form of this characteristic that we show on this screen. Now, there are really three settings that describe how we build these curves. One of the settings is the curve type, and it will describe the shape of the curve. I'll talk about that in a few minutes. The other setting that's important is the actual pickup setting. So the pickup setting, the current has to be greater than that pickup setting before we start to operate. And so we see pickup on this graph as the dotted line there. The other setting that is important for this is the time dial setting. And the time dial setting describes how high or low the curve actually sits on this time current characteristic. And so we can use those settings to manipulate the curve and get coordination between two devices. So if we think back to the screen that we just saw, we had the main feeder relay and feeder relay 3, and feeder relay 3 is electrically downstream, the main feeder relay, so it's being fed by that relay and that breaker. And since it's been fed by that breaker, we want it to trip faster than the main feeder relay. So we build these curves, we set the time dial, and we set the pickup such that it time coordinates with the main feeder relay. Now we can't put it just below the main feeder relay, and I'll talk about that, why we can't do that in a few minutes. We want some margin between those two curves. And so that margin is called the time coordination interval or the coordinating time interval. So I may use those two terms interchangeably. But you can imagine now, so if you look at the fault at F1, so the red line there at F1, so that's a particular fault current with current along the x-axis and time along the y-axis. You can see that the curve on feeder relay 3 is going to trip feeder relay 3 before we get a chance to trip the main feeder relay, which is what we want. So to sort of look at that on the actual power system, those two graphs can be represented on the power system. So you can see if we barely overreach the breaker at feeder B, and we move up in time along the y-axis, we would trip the breaker at feeder B before we trip the breaker at the main or breaker A. Okay, so I mentioned earlier that one of the settings that is very important is the type of the curve. So here are some of the types. There's multiple types of curves. There's ANSI curves, there's IEEE curves, there's even some NEMA curves. Most of these curves are supported inside of our devices, but I think these are probably IEEE or ANSI curves. But looking at these, there's an extremely inverse curve, and it has a slightly different shape than the very inverse curve, which has a slightly different shape than the inverse curve. So these curves sort of help us to, the shape of the curve helps us to sort of build up the curve and to start to coordinate with things. And we'll see in a few moments, I'll come back to this, but the extremely inverse and the very inverse help us coordinate with fuses very well. Now, the next thing that is sort of important for us to set is the pickup. And as I mentioned, the pickup would be where the curve just starts to pick up. So below that current, we are not timing. Above that current, we are timing against the curve. The other setting that is really important is the time dial setting or the time multiplier setting. So the time dial setting will move the curve up and down the time axis. So a smaller time dial setting moves the curve down the time axis, and a larger curve or a larger time dial setting moves it up the time dial axis. So if we look at the curves here, you can see the smaller time dials are on the bottom, and then the higher time dials are on the top. And these are all the same curve, the same pickup setting. A third option that we might employ is a flex curve. So flex curves are curves that you can basically customize and build inside of the relay. So the 8 series relays and the URs have the ability to build these flex curves. And basically what you do is you enter, to build the actual curve, you enter a multiple of pickup and a time to trip. And so what this does is let you build a custom curve that kind of exactly coordinates with certain devices. So the device that we show dashed here is some type of fuse there, and we are building a curve that exactly coordinates with. This can be helpful when we've got static trip devices, we've got fuses, molded case circuit breakers, or transformer damage curves that are a little bit non-standard and we want to exactly coordinate with them. Okay. Colleen, could you advance my slide? It's not advancing for me. Okay. So let's talk about coordination and how we coordinate these devices. So here is a typical coordination curve. And so this probably comes from something like ETAP or Easy Power. And you can see the curves in there. And so what we're going to have to do is we're going to have to stack up our curves so that they coordinate, and we don't have areas of miscoordination. So ETAP and Easy Power make this very easy for us, and those are both some modeling software that helps us to model our power system and also to coordinate things. It'll also do things like do arc flash studies for us. But nonetheless, some of the things that we've got to do, if we look at this particular slide, there's a transformer right in the middle of this power system. So not only do we need to coordinate the things downstream from that power system, from that transformer, we also need to coordinate upstream from the transformer. We'll have to coordinate across the transformer. And then the other thing that we probably need to do is if we look at the little X that's just above the flat portion of the blue curve, that is the transformer inrush. So for those downstream devices, we will need to be below, or for the upstream devices, we will have to have a slower tripping time than the transformer inrush. Likewise, the curve that is at the straight curves there are the transformer damage curves, or the transformer thermal damage curves, and we'll need to have all of our protection devices set so that we are below the damage curves and we don't damage the transformer. So let's look at some of these mechanisms and some of these curves. So one of the things that we often will have to coordinate with is with fuses. And if you look at the fuse curve that I show here, the fuse, it looks very different than the curves we've been talking about up until now. And the reason it looks different is a little bit fatter, is that it has a minimal melt and a total clear associated with it. So the minimal melt is the time for the fuse to be damaged and start to melt. And then the total clear time is the time for the fault current to be totally cleared by the fuse and the fuse barrel. So you can imagine if we are coordinating other fuses, or we're coordinating relays that are either electrically downstream or upstream of this fuse, the things that are downstream, we want to coordinate on melt time so that we don't infringe on that minimum melt time and blow the fuse or a fault that's below a relay or below another fuse. Likewise, we want to coordinate devices that are upstream with the total clearing time so that we totally clear the fault with the fuse rather than tripping those upstream devices. So to put this into perspective, if we look at this sort of scheme here where we've got a circuit breaker with a relay on it, so we've got a relay curve there, and then we've got a couple of fuses downstream. We want to stack those fuses up so that the fuses aren't going to, I'm not going to start to melt fuse F5 before I totally clear the fuse at F2. And likewise, the fuse at F5, I want it to totally clear the fault before I get into, or I start to infringe on the relay overcurrent curve. And in fact, I want some time between those devices to ensure some margin and to make sure that I don't overtrip. So here's another example of coordination between the fuses. So again, like I said, I want to make certain that the two fuses don't infringe on each other and that there is some time between them. Now, when I say infringe on them, you can imagine if the minimum melt curve of the green curve, if it overlapped with the total clear of the orange curve, what would likely happen is if I had a fault below the green curve, I would probably, if I had a fault below the orange curve, I would probably trip both devices, because before I could totally clear the orange curve, I would get into the melt time of the green curve, and that would cause me to overtrip and trip more than I absolutely had to. But in reality, we want some margin between the devices, or between the curves of the devices. And so we call that margin the the coordinating time interval or the time coordinating interval. So I show that time coordinating interval here with the time overcurrent curve of about 400 milliseconds. Now in a few minutes we'll go through why we think this should be around 400 milliseconds, but you want some time. And there are a lot of things going on there and with relays that we need to coordinate some time with. Now one of the things about fuses is that the fuse itself will be subject to manufacturing tolerances associated with the fuse. So because of that, and because we can't really test the fuse in a non-destructive way, typically the time coordinating intervals for a fuse will be longer than the time coordinating intervals for a microprocessor-based relay. Likewise, if we have an electromechanical relay, which can drift and have shift in it and needs calibration, we typically will have a longer time coordinating interval, or we would want a longer time coordinating interval than if we had a microprocessor. So here's a typical curve. So the red curve is a typical microprocessor-based relay. Orange curve is a fuse curve. And then the dotted blue curve is another microprocessor-based relay. And you can see here that between those two microprocessor-based relays, we're getting a 300 millisecond coordinating time interval versus the 400 millisecond coordinating time interval that we want between the microprocessor-based relay and the fuse. Now again, the reason we can go smaller with the coordinating time interval between the microprocessor-based relays is simply because those devices are microprocessor-based. They're a little bit more accurate than the manufacturing tolerances of fuses. And we'll talk about why we use these numbers in just a couple of slides. But the next slide shows an example of what happens when we have miscoordination. So this is an area of miscoordination. Not only do we infringe on the coordinating time interval, and not only do we not have the coordinating time interval, if we look at the main feeder relay and feeder relay 3 being the black curve, and the main feeder relay being the blue curve, you can see that for fault currents at F2, so the red line there at F2, and then even F3, we're probably going to trip the main feeder relay. Now, if the fault current below feeder relay 3, if that fault current if the available fault current isn't greater than F2 or F3, that's probably not an issue. But in most instances, that's an issue based on these curves and where those curves are getting flat. We probably can see that fault with both of these relays based on where they're at. And if that's the case, we're going to trip the main relay before we trip feeder relay 3, which means we would overtrip. So we need to take care of that coordination problem. So the way that I would probably take care of this problem that we see here is I would simply raise the time dial setting. So I would raise the time dial setting on the main feeder relay. And remember earlier I said that the time dial setting moves that curve up and down the time axis. And the time axis is the y-axis we see over on the left. And so by increasing that time dial setting, I can take care of the coordination problem, the miscoordination problem, but then I can also get back to the coordinating time interval that I need and I desire so that I am coordinating properly between these two devices. So what are good coordinating time intervals? And this is a very openly debated topic and a very hotly debated topic. I mentioned that with fuses, we probably want around 400 milliseconds. And the reason for that is because we're subject to some of the manufacturing tolerances of the fuses. We can't really test the fuse in a non-destructive way. So let's look at electromechanical relays versus microprocessor-based relays, and the typical types of errors that we would see, or the types of things that we need to account for with these coordinating time intervals. So on electrical mechanical relay, we can have a larger basic metering error than we could on a microprocessor-based relay. So we're showing a 7.5% error there, and so a lot of that will depend on how well calibrated the microprocessor-based relay is. You know, if we think of this as something like an IEC relay, which is an induction disk relay, there's calibration that needs to take place, and over time that calibration can drift. That's why we have such a much larger basic timing error that we're accounting for, or we're budgeting for in this CTI with the electromechanical relays versus the microprocessor-based relays. There's also the issue of overshoot. So in an electrical mechanical relay, the overshoot is really around inertia. If we have a disk that is turning on an IEC, if we immediately stop the current, there is still some inertia that is moving that disk forward. So we have to account for that, especially if it's really close to tripping. Now, we don't have a disk that moves in a microprocessor-based relay, but remember I said earlier that the way that we're going to actually calculate quantities is we're going to take samples of the waveforms that are attached to the relays and then use something like a Fourier transform to turn those sampled values into a magnitude that we could then run through a comparator to operate. And the issue there is that a Fourier transform is a summation type function. So if we immediately stop the current, there will be some small time before the relay starts calculating that it's zero. Or if the current drops below pickup, there is some small time that it will take for the relay to recognize that. So we're counting for 20 milliseconds for that. And then there's the issue of a safety margin. So a safety margin is just a margin to ensure we're safe. And so this safety margin is also where we'll include things like the breaker operate time. So we'll account for the breaker operate time there. And so typical coordination times then come to something like 400 milliseconds for a electromechanical relay or 300 milliseconds for a microprocessor relay. One of the other functions that we should talk about also when we're trying to coordinate devices is a reset. Now this is not as important in an industrial distribution facility as it is a utility distribution system. So when I say utility distribution system, what I really mean is overhead medium voltage distribution on wooden poles. And the reason that's the type of reset is important there is because we will have reclose on these sort of devices, on these sort of systems. And so there's two ways that your relay can, a microprocessor-based relay can reset. It can instantaneous reset, which that means as soon as the element drops out, all the time delays drop to zero, or all the timers drop to zero. And if you have nothing but microprocessor-based relays in your distribution system and microprocessor-based devices in your distribution system, that's the appropriate way to do that. However, if you're coordinating microprocessor-based relays with electromechanical relays, you should set that to a timed reset. And what the timed reset does is it sort of mimics the functionality of the disk in like an IEC relay. So you can imagine an IEC relay, electromechanical relay. If it sees a fault, it has a disk that turns. And if it gets close to tripping, but the downstream device trips, that disk will take some time to turn back to its reset position. And if you have subsequent reclose shots, you can basically ratchet that disk into an area where you could cause a miscoordination problem. So for that reason, if you're coordinating microprocessor-based relays with electromechanical relays in a distribution system that has reclose, you should use the timed reset. Okay, so let's talk about some GE solutions for overcurrent protection. So the four main solutions that I should talk about today are the 3 series, the P14 series, the 8 series, and the UR. So as I move from left to the right, from the 3 series to the UR, I'm moving up in functionality. So the way that these relays are sort of broken up, the way our relays are broken up, is by a product family. So the 3 series is a product family that is meant to be very cost effective and low function and easy to set. And the variant in that family that does feeder protection is the 350. Now the 3 series also has a transformer protection relay, the 345, and a motor protection relay, the 339. The second relay in this family is, or the second family of relays is the P14 family. And so the P14 has been around since 2014. Both the series and the P14 are of draw-out construction, and both are families. So the next relay in the series is the 8 series, or the next family in the series, the 8 series. So the 8 series is, I would say, fairly new, but 2013 seems like a long time ago now. And so it's been around since 2013. So the 8 series is sort of our workhorse industrial platform. So it is targeted to industrial customers, but it's also targeted to those customers, utility customers for overhead distribution, just like I mentioned. And I've got a couple slides that I talk about that in the next slide or so. But the 850 has several variants. There is the 850, which is the feeder relay. The 8 series has several variants. There's also an 850P and an 850D that I'll talk about that are targeted to the overhead distribution market or the utility distribution market. But then there's also an 869, which is a motor relay. There is a 845, which is a transformer relay, and an 889, which is a generator relay. Again, these are the workhorse platforms for industrial and utility distribution. So as you can see, this relay has multiple push buttons, which give you the ability to control your equipment or control the relay from the relay itself. So you don't need discrete, or you don't have to have discrete 01 for operating the breaker, or discrete 43 switches for choosing options in the relay. This relay also has a large graphical faceplate that helps you to operate as well and helps you to mimic the real world. The next family, moving to the right, is the UR family. The UR family is our workhorse family for transmission and generation. The 2 variants in that family that are targeted to feeder protection are the F60 and the F35. All the relays prior to this were draw-out construction. The UR is modular construction, and the UR has been around since 2001. I think that's a little wrong. I think it's because I put the first UR in that I ever put in the year 2000. But we are on the 3rd hardware version of the UR, and the form factor is the same. The only thing that's changed is the modules that are inside the UR in the last 19 years. So 2 of the sort of differentiators that we should talk about for the 850 and the utility market, the distribution utility market, are the 850D and the 850P. So I'm going to go very fast because I want to leave some time for questions. But the 850D can do a single feeder protection just like we normally do with those sort of feeders. But we can also do a dual feeder protection like I show in the middle. This relay has enough inputs to have CT inputs for 2 different breakers and enough voltage inputs for 2 different feeders. So this sort of lets us do something on the far right that we've never had before. It lets us do redundant feeder protection with no more relays than we would have had to have with the single feeder protection that we typically do today. And the last variant that I probably should talk about in the 850 platform is the 850P, which is targeted for pad-mounted switchgears. And so this device can protect and control with a single device a 4-way pad-mounted switchgear, like we show here with 2 feed ways and 2 load ways. So it can do the 4 feeders in this 4-way switchgear with a single device. And since it has logic in it, we can use that single device then to not only do the protection, but to do the throwover scheme. So let me conclude so we've got some time for questions. So I will say that for overcurrent protection, we need to time coordinate those devices so that we don't overtrip. When we are coordinating devices, we need to account for the performance of our devices with our coordinating time interval. And lastly, I spent some time on ground protection, and the type of ground protection that depends on your grounding type. And with that said, I think we have some time for questions. Colleen, would you care to remind everyone how they can ask a question?
Sure can, Terry. Just a reminder, if you do want to submit a question, please click the Q&A widget at the bottom of your screen. Type your question in the text field and click Submit. Terry, I'll turn it back over to you to begin answering the questions that have already come in.
Okay. So one of the first questions is, can we share the slides? So I think Colleen will send a link out afterwards that will be a link to this recording. Is that correct, Colleen?
Sure is.
Okay. Okay. So one of the questions is how do we count for poor breaker maintenance in a coordinating time interval? So I would say that what we need to do there is, well, first of all, we probably ought to have better breaker maintenance. But beyond that, we typically account for the poor breaker maintenance and the fact that we might have a 3-cycle that actually takes 5 cycles, a 3-cycle breaker that actually takes 5 cycles to operate. We account for that performance. We count for that performance with the safety margin. Okay. So there was a question about the what about the 7 series relays? So you're probably referring to the 750 relay. The 750, but the family of relays that the 750 falls in 745 is the SRs. So there is an obsolescence notice that was published on the SR relays, which would include the 750s, the 469, and the 745, and that was published a year or so ago. It's been a while that publication was published. So the last buy window on those relays is in December of this year. So what I would suggest doing is there is a retrofit kit that's available to retrofit those SRs into an 8 series. And so there's a great video on that in our resources page. Whoever asked this question, I should send you a link to that. But basically what that looks like, or what that feels like, is you take the terminal blocks off of your 750 case, and those terminal blocks will plug into your 8 series retrofit case. So basically you take those terminal blocks off the 750 case, you take the relay out of the 750, you do all that after you've de-energized and followed your company's policies. You take the case out, put the 8 series case in, plug the terminal blocks back into it, the 8 series into the case, and re-energize the relay. And then there's a mechanism inside of 8 series setup that allows you to convert the settings file. So you can take your 750 file and convert it to your 850 file, and then you can put that in your relay. So that allows you to sort of replace those relays with minimum disruption to your wiring. Okay. Oh, there's more that came in. So the question is, could you provide an example to calculate negative sequence phase or ground pickup values? So what I would say there is ground pickup values is you should do that in a similar way that you've calculated or done your phase pickup values. So you need to calculate for your phase pickup values. You're basically going to calculate your maximum phase current, 3-phase current, or and then you're going to determine how far for a phase fault do you want the thing to reach, or how far into the power system you want it to reach. And you can do that with your, sort of your pickup settings. So you're going to do the same thing for a ground overcurrent or even a neutral overcurrent. You're going to calculate your available fault current, and you're going to make a decision around pickup on how far into the power system you want it to reach. So typically on both of those, you want it to reach as far as possible, because that way it can provide backup to other devices, but then you have to coordinate them. Negative sequence is a little bit more complicated, because typically with negative sequence, what you're wanting to do is you're wanting to trip for something like a open phase or a or a loose conductor or things of that nature. So the challenge there is you always want to set that large enough that you're not going to misoperate because of CT accuracy issues. But you want to set it small enough that you can catch those sort of. Okay. So next question that I see is, what is the difference between ANSI and IEC curves? They are different shapes. So this goes hand in hand with, I guess, the next question I see there. But the ANSI curves and the IEEE curves and even the IEC curves are defined by those standards bodies. So if you go to our instruction manuals, you can see the formulas to calculate each one of those curves. So that's sort of the difference between the two. The question that's very similar to this, that's just right above it, is what is the best way to calculate trip times from standard curves? So the most difficult way is to take the formula that I just mentioned in the instruction manual and pull out a calculator and do it that way. The way that I've done this in the past is I've implemented that formula into an Excel spreadsheet, and that's a good way to do that, because you can then see that the trip time for several different multiples of trip on a spreadsheet, and that can help with testing. what a really cool hack that I usually use to figure out the trip times for a curve is, I mentioned the flex curves earlier, so I can go to any relay setup software that has a flex curve, like the 8 series or the UR, and I can go to those flex curves, and there's a functionality in there to initialize the curve from a standard curve. So I could just pick whatever standard curve I'm wanting to look at, and I can click on initialize from that curve, and then it will populate, trip times based on that curve. And that's a hack that I typically use to do that. Okay. Make this a little bit bigger so I can read this. Okay. Okay. So there's a question around the ability to convert 845 settings file, or not 845, but 745 settings files to the 845. And the question is there a limitation while converting the different firmware versions of the relay? The conversion actually does is when you do it, it's not, what you're actually doing is when you're building the 8 series settings file, there's like a checkbox that says, do you want to, I don't remember the exact words, but it says something like, do you want to instantiate this file from this other settings file? And you can click yes, and then you can browse to wherever that file is on your laptop using the tool. And when you do that, it's going to build the 845 as close as it can. Now, it's going to know what firmware version you're using in the 745 because that's a portion of the settings file, and so it'll instantiate from that. One of the key things that I will point out is that when you do convert that file or instantiate that file, you get a conversion report. And what that conversion report does is it will tell you any settings that are different. So settings that are different, there will be a lot of settings that aren't necessarily different, but there'll be new settings. So the 8 series has a lot more functionality than probably the 745 that you're replacing it with, and because of that, you'll see some things flash or targeted in that report that you might want to look at. A lot of the things are things that it's just making you aware that those settings weren't in the 745. Some of the things, and they'll show up either yellow, green, or red. And the things that are red are things that you really need to look at. Question, does P14X really have the capacity? Does the P14X have the ability to support dual and redundant feeders? That, what I was saying there was the 850D and the 850P. That functionality isn't really in the P14. So, does the TCAI, coordinating time interval, account for breaker operate time at 3 cycles? Yes. So typically the breaker operate time is covered inside of that safety margin. Is the time delay setting used for the coordination between relays? Yes, so if we have definite time delay elements, so if we have an instantaneous element and we want to set it as a definite time delay, then yes, we could set that definite time delay to coordinate between other definite time delay elements. The other thing is if we have a time over current curve, we can use the time dial setting to coordinate between devices. And there's a really complex question here about reclose and saving the fuse, and I'm probably not going to get to that one, but I will answer that question via email. Some of these questions I don't think I can get to today because we're right at the top of the hour. So I will have to reply to some of these questions via email later. And with that, I think I'll invite Colleen to have her concluding remarks.
Thank you, everyone, for attending today's webinar. This concludes our session. Thank you so much, and have a wonderful day.